So Mary Mahler, she did her PhD with Jens and Sarah at UCL, and now she's at the Ethereum Fund. She'll give us on inner product arguments. Take it away.
Oh, thank you. Can everyone see my screen okay? I'm not sharing a random browser or whatever. Awesome. So today I'm going to be giving an overview talk. I'm going to be talking about inner product arguments, a lot of the historic literature, as well as some of the more recent literature, and trying to sort of place it all. This will include some of my own work, but it won't be entirely. So just sort of start off with the basics. What is an inner product argument? In the explanation I've given, I'm saying that we're taking in 4 inputs to each of these commitments, A1, A2, A3, A4. Actually, this could go up to any number of inputs, n inputs, but I thought it looked nicer on the screen with 4 inputs. So the basic aim of an inner product commitment is you have 2 commitments, 2 vector commitments, one to one set of inputs and another to another set of inputs, and you have an evaluation, and you just want to prove that you can open these commitments to 2 different vectors such that the inner product of the first vector with the second vector is equal to that evaluation. That is the aim. In some ways, this can be seen as a special case of the sum check protocol, is a recent result by Bootle et al. So there was a breakthrough work in 2016 when it comes to inner product arguments, where Bootle et al., different et al., computed a logarithmic sized argument in the discrete logarithm setting without a trusted setup. And the key insight to their algorithm, this was the first log size zero knowledge argument, by the way. Before then, or at least for general purpose arguments in the discrete log setting, before then it would have been square root. So they broke that square root barrier by using a recursive method. So the basic idea is you start off with the problem that you're trying to solve. You have 3 commitments, each of which are 2 of your commitments are containing 4 values, and you want to prove that C equals A1, B1 plus A2, B2 plus A3, B3 plus A4, B4. Rather than proving this statement, you instead prove that if some other commitment contains A1-B1- and A2-B2- such that their inner product is equal to C-, then the original statement, C equals A1-B1 plus all of that must hold. And then you apply the same trick again, and you say, okay, we've got these commitments with 2 inputs. What happens if we fold them down to a commitment with 1 input? And then we're going to prove that if A1 double dash B1 double dash equals C double dash, then C dash equals A1 dash B1 dash plus A2 dash B2 dash. So because if the first statement holds and the second statement holds and the third statement holds, and we've proven the whole thing. And then just at the end, in order to show that the last statement holds, you can open the commitments because that's a single value and is very cheap to do. So about a year or so after this result came through, Boons et al. Improved the efficiency of the argument by a factor of 3 and showed how to apply these inner product arguments to range proofs. And the argument which they've come up with is being used a lot in range proofs today. I believe that Monero has an audited implementation as well. They basically, their trick is to say, okay, rather than having 2 commitments and an evaluation, why don't we have just 1 commitment which commits to all of the values and the evaluation at the same time, and then run the folding argument on that combined commitment. These 2 arguments are both being applied to a wider scheme in order to get a zero knowledge argument, but they are not zero knowledge themselves. They could be revealing all sorts of information. So for the particular case of the Boons et al. Argument, we can actually get zero knowledge based on adding some randomization that Hoffman and others showed how to do. The results of this, by the way, do not apply to all inner product arguments. And in particular, you couldn't use the results on the Bootle et al. Proof, because in this situation, they're revealing one of their evaluations in the clear. So just by revealing that evaluation in the clear, already you have revealed some information. So if you want to then use the result in the zero knowledge argument, you have to add randomness elsewhere. But in the case of the Boonton et al. One, you can add the randomness straight from the get-go. Their argument they do two things. They first show that they have enough randomness, but they also show that the different ways in which you linearly combine the randomness throughout the different steps of the recursion doesn't result in any of that randomness being cancelled out at any point in time. There are two other works which I'm aware of, there's probably more, which are using inner product arguments in the discrete log setting. The first one is Firex, and basically they took the inner product argument of Bootle et al. And one of Boonton et al. And they said, okay, in your situation, you have one commitment, which is committing to all of your values at the same go. This is great. It produces a small proof, but your verifier time, that verifier time is linear. This is often a problem. We don't want linear time verification. So what they instead decide to do is they work with commitments which are square root sized. So again, you get larger proof sizes again, but because the commitment sizes are square root sized, they're then able to make the inputs to the commitments square root sized, such that when it comes to checking the verification at the end, where they're opening up the commitment, that is a square root opening, and they can check all of their rescaling has been done in square root time. So the verifier is square root time. Firex didn't actually manage to get a full zero knowledge argument for any general purpose language. They could only do it for very specific languages. So Spartan, which we heard about earlier this week, improved on that result by being able to extend it to any circuit. When it comes to discrete log settings, we can also make improvements if we have a universal setup. So again, this is if we have some parameters which are in some way correlated, which we've generated using a trusted setup. Their results apply not in the publicly verifiable model, but they are able to make improvements in the designated verifier model, and also in a model which I'm calling the helper model, which is what we called it in Sonic, but I feel like there is a better term for it somewhere which someone knows, which isn't me. The idea here is that once you've produced all of your proofs, you have another party comes along who takes all of the proofs and they aggregate them. And this aggregation is not to reduce proof size, the proof size stays the same, but it's to produce an advice string which can be used in order to verify the proofs much more quickly. So they say that if you have some party that's willing to do this, some helper who produces the advice string, then you can get logarithmic verifier time for everybody else in the system. So far, all of the schemes I've been mentioning have been secure in discrete log groups. You can also build inner product arguments in bilinear groups, and Lay, Malavolto, and Runge in particular do this. So they say that we can prove that a set of pairing arguments has been applied correctly, such that we have a correct pairing evaluation. We have also worked on a topic which is very related to this, in that we have been saying, okay, we have this inner product argument, this sort of generic folding method. It doesn't just apply to discrete log groups. We know for a fact it also applies to parent groups. We know that it can apply if you have different sized commitments. We know that it can apply if you have some parts of your commitment in a parent group, some parts of the commitment in a discrete log group. So we were then like, okay, we have many different security proofs for the same scheme. Can we generalize this? And the answer is yes, we can generalize it. We have a generalization with a security proof that should hold across these many different works, as well as an implementation in the ArcWorks library, which you should just be able to pick up and use for any inner product argument sort of that fits the requirements. And when it comes to applications where a universal setup is acceptable, which, you know, I think there are a good number of applications where this would be true. Maybe not if you had to have a separate setup for every single scheme, but if it's a universal setup, then we can get very good, I would say, practical efficiency in some settings at least. One of the big ones is when it comes to aggregating Grot16 proofs. And here we're able to aggregate 130,000 proofs in the same time that prior works were aggregating 90 proofs. And the reason for that speed up is because we're not doing a reduction to an NP circuit, we're just sort of proving it directly using a sort of native scheme. Likewise, we're able to get polynomial commitments with very, very good proof efficiency, logarithmic proof sizes, fast logarithmic verification, and a square root sized SRS, which is different to the KCG scheme, which has smaller proofs, but a much bigger SRS and linear prover time. For the Grot16 proofs, we're also able to apply these results to machine computations in order to get a machine computation which doesn't use as much space. So improving on our work is when it comes to the trustless setup setting. So when you want to have a public coin setup, is a breakthrough work by Jonathan Lee, a work called Dory, where Lee is able to construct a logarithmic sized logarithmic verifier in a product argument in bilinear groups with a public coin setup. And the basic way in which this is done is being able to prove that the rescaled commitment keys at each step has been done correctly. And this can also be used to generate a zero knowledge argument from a public coin setup with logarithmic proof size and logarithmic verifier. Still concretely more expensive than other snarks because we have target group elements which are quite heavy, but equally sort of much, much smaller than anything where you're talking square root size proofs. So if you're willing to make a trade-off between proof size for your public coin setup, then this is a scheme which allows you to do that. One of the last two works I'm going to mention is Halo, which I'm sure we've heard about this week a lot. So in Halo, what they're able to do is they're able to use curve cycles inside a discrete logarithm group with no pairing at all, together with an inner product argument in order, again, to generate a zero knowledge proof. And because they're using a recursive method where they're saying, we're going to prove a proof of a proof of a proof of a proof, the amount of work that the verifier does depends only on the recursion threshold plus a logarithmic quantity rather than on the size of the circuit. So a big advantage of this is it means that they don't need to worry about pairings and they can work. And it also means that they don't need to worry about trusted setup and they're able to come up with something which is also, I think, very elegant. All of the schemes I've mentioned so far are proven in the interactive model. And then there's this sort of hand wavy argument which says, and we apply the Fiat-Shamir transformation in order to make the schemes then actually okay when we use them in the non-interactive model, which is when everyone would want to use them. The only alternative of this that we are aware of is an algebraic group model proof. This is something that we've also worked on in our paper, but Goshal and Tessera are able to get some fairly concrete parameters and exactly how efficient their extractor is. And they're able to work in a setting where the extractor possibly has information access to lots of information about the system. So they do a very thorough proof that this technique works. And I would actually say that this is more important than it might seem at first, because in some ways you're there thinking, okay, Fiat Shamir heuristic, no one's really broken it, it kind of works. But actually the standard Fiat Shamir transformation would not apply to all folding arguments if they reached a certain size, okay? So that if they reached a certain size is a sort of big catch, because the extractor in the interactive model, you can only do a logarithmic number of rounds, because otherwise you wouldn't be able to extract efficiently. But maybe when we're talking about recursion, and we're talking about not only this logarithmic size recursion, but also a recursion inside a recursion, you then might end up in a situation where you have more rounds than maybe you had accounted for. And if you get to a situation where you have a linear number of rounds, then a recent attack on an ROS system, which has been sort of applied extensively to lots of different threshold signatures, would also be applicable to these inner product arguments. So I'm not saying there's an attack here, I don't think there is, but I am saying that this might not just be a theoretical detail, there might be something real going on here. That concludes my talk. Thank you for listening.
Virtually thank the speaker. Any questions? Maybe Manuela, you can start presenting well.
Yes.
So that last point about the ROS attack, suppose pessimistically that attack works completely and there are no obstacles to it. What would the cost of the attack be?
So if there were no obstacles, very, very fast, like I can run it on my laptop fast. But it is completely broken if you hash the transcript as you go, then there is no way in which it would work. But hashing the transcript as you go is something which is picked up that, oh, you should do this in the algebraic group model proof. It's not picked up in the interactive model proof.
Okay. I'd always assumed that was part of the Fiat Shamir transform in general.
Well, no one's really applied Fiat Shamir to these recursive protocols where you have sort of, well, no one's done it other than sort of saying, oh, you can do it. Like, probably if you went through very carefully, you would find that you needed to do this. Certainly, if you just apply it, then because people are thinking about 3-round protocols where you wouldn't be worried about messages from round 1 because there is no round 5, then I don't know that you would necessarily pick up on this.
Okay.